In this lecture, we'll be dealing with the mean value theorem. Before we get into the mean value theorem, we want to have a few definitions for functions, specifically what it means for a function to be increasing. A function f is increasing on the interval ab, provided that f of x1 is less than f of x2 for all x1 and x2 in the interval I, such that x1 is less than x2. Sometimes this is also called strictly increasing. If you think about this definition, we can see how it will sync up nicely with our intuition. So if this is our interval AB, then this definition says for any pair x1 and x2, such that x1 is the smaller, so let's take x1 here and x2 here. If you feed these x1 and x2 to f of x1 is lower than f of x2. So here could be f of x1, and here could be f of x2. What this theorem, or what this definition says, is that for any pair x2, so slide these back and forth, if you evaluate f at the left one, you'll always get something smaller than if you evaluate f at the right one. That's what it means for a function to be increasing. The result of that is your function is going up on the interval ab. The definition for a function decreasing, everything in this definition is exactly the same as the increasing definition, with the exception of this is a greater than or equal to, or sorry, a strictly greater than sign. So it's the reverse of this. Anytime, so yeah, here's our increasing picture. And for decreasing, if we're on the interval AB, here's your smaller of the two, x1. Here's your bigger of the two, x2. If you feed x1 to f, you get something larger than what you get if you feed x2 to f. So up here, we have f of x1. Actually, we want something bigger. And down here, say, is our f of x2. And if you slide x1 and x2 back and forth, it's always the case that f evaluated at the left point is higher than f evaluated at the right point. That's what it means for the function to be decreasing on AB. And it's important to recognize these definitions don't depend on a function being differentiable. They don't depend on the function being continuous. This is just capturing the idea of going down for decreasing or going up for increasing. A slightly more general definition is if we add the term monotone. And you'll see this definition for a function being monotone increasing is the same as the definition of being increasing, or strictly increasing, except we have a less than or equal to. And the result is that for an increasing function, the function is always going up, but if you're monotone increasing, it can have flat spots. So for a monotone increasing function on an interval AB, you may be going up, but you can level off and then continue going up. We can't go down, but we can level off. And for monotone decreasing, it's the same principle. You're going down or leveling off. Now, if we add the caveat that f is a differentiable function AB, then it turns out that f prime of x being positive on AB is the same thing. It implies that f is increasing on AB. If f prime of x is negative on AB, that implies that f is decreasing on AB. Let's draw a case where our function has a positive derivative. What does that mean to have a positive derivative? It means that at any given point, the tangent line, the slope of the tangent line is positive. And so to draw a function that has this property, it has to always be going up. It has to be always increasing. That's the only way we can make sure that the tangent line at any point is actually positively sloped. Similarly, if a function is decreasing, or rather I should say, if f prime of x is negative on our interval AB, then at any point the slope of the tangent line has to have a negative slope. And the only way that can work is if the function is in fact decreasing or going down on that interval. Now this is actually a result of the theorem, the mean value theorem, which is the main subject of this lecture. In order to work our way up to the mean value theorem, we have Rawls' theorem, which we use as a lemma in the proof of the mean value theorem. So we'll state Rawls' theorem and then work through the idea, though we won't prove it. So Rawls' theorem says, suppose that f is continuous on AB, closed interval AB, and is differentiable on the open interval AB. If f of A equals f of B, then remember backwards capital E means there exists. So there exists a value C in the interval AB such that f prime of C equals 0. Seems complicated, but when we draw a picture, this becomes quite a bit simpler. So suppose we're here on the interval AB. And the key thing to start with is that f of A is equal to f of B. So if we evaluate f at A, we get the same value that we get if we evaluate f at B. Many calculus books will say f of A and f of B equals 0, but you don't need to be that specific. They just have to be the same. Now, the other key properties of f, they're continuous on the closed interval A. F is continuous on the closed interval AB, and it's differentiable on the open interval AB, which means as I draw f going from f of A to f of B, I have to do so in a way where the pen touches the paper. It can't leave until I get to B, f of B. But it also has to be done in a smooth way because f is differentiable everywhere in between A and B. So let's think about what that means. It tells us there has to be some value C in between where f prime of C equals 0. What does it mean for f prime of C to equal 0? That means the tangent line at x equals C is horizontal. So if we draw this and we're drawing it in a smooth way, sooner or later I got to turn around and come back down Now there's many ways you could draw that, but there's only two possibilities. One, either I drew it as a straight horizontal line from this point to that point, in which case the tangent line is horizontal at every point between A and B. If instead, as we did in the picture, we deviated from that horizontal line connecting these two endpoints, well, here we went up, which means sooner or later we had to turn around to come back down. And we had to do it in a smooth way because the function is differentiable, which meant that at that turnaround point, and there had to be at least one, the tangent line is horizontal. And remember, if a tangent line is horizontal for a differentiable function, that's the same thing as the derivative being 0 at C. So this would be our C, where the derivative is equal to 0. We can see Raoult's theorem in an example. If we're given f of x is x squared minus 2x on the interval 0, 2, let's find a C that satisfies Raoult's theorem. Well, we know f prime of x is 2x minus 2. And if we set f prime of x equal to 0, we get 2x minus 2 equals 0, 2x equals 2, or x equals 1. And so this is telling us, if we're looking on the interval 0, 2, f of 0 is 0. F of 2 is 2 squared, or 4, minus 2 times 2, which is 4. So that's also 0. And we can check, by the way, if we plug in 1, f of 1 is 1 squared, which is 1 minus 2, or negative 1. So we know we have this point down here. And Raoult's theorem has told us f prime of 1 equals 0. So this function has to look something like this on this interval. We have the horizontal tangent line at x equals 1. So this is our C that would satisfy Raoult's theorem in this example. So again, that's because f prime of 1 equals 0. So that's Raoult's theorem in action. Again, the main reason that we introduce Raoult's theorem is because we use it as a lemma in proving the mean value theorem. And so this is one of the most important results in all of calculus. I usually think of it as having three main results in calculus: the mean value theorem, the fundamental theorem of calculus. You see that when you study integral calculus, and then Taylor's theorem, which you see when you study infinite series. The mean value theorem says the following. Suppose f is continuous on the closed interval ab and differentiable on open ab, then there exists a value c in open ab such that this equation holds. F of b minus f of a equals f prime of c times quantity b minus a. This is a lot to take in when we first see it. And the key to this is to understand the geometry. So let's draw the picture, and then being such a critically important theorem, we will prove it. So we're working on the interval AB. Our function f of x is differentiable on AB, and so we have to draw it in a smooth way. Suppose down here we have f of a, and then up here we have f of b. Now again, we have to draw the function in a smooth way connecting the points. Why don't we name these points? This will be the point P, and this will be the point Q. So P is the point A, f of A. Q is the point B, f of B. So we connect these 2 points with a smooth curve. That's our function y equals f of x. Now, let's draw the line that connects PQ. So that line we're going to call PQ. And let's start to think about slope of that line. So what is the slope of that line? Well, we want rise over run. Run is nothing more than b minus a. Rise will be f of b minus f of a. So the slope of PQ, the line, is rise over run, or f of b minus f of a over b minus a. Take note that if you were to take this equation 1, and divide both sides by b minus a, this is what you would get. So the mean value theorem, rewritten, has f of b minus f of a over b minus a. Again, that's the slope of line PQ. That's equal to f prime of c. So what does that mean? Well, the mean value theorem is asserting the existence of a point C in the interior of AB such that this equation holds. This expression in orange is the slope of the tangent line. Sorry, this equation in orange is the slope of the line PQ. F prime of C is the slope of the tangent line at C. So what this is saying is there has to be a point C where the slope of the tangent line, or an x value C, where the slope of the tangent line is the same as the slope of PQ. So the tangent line at x equals C is parallel to the line PQ. So what this is saying, again, there must be a C in AB such that the tangent line at x equals P, x equals C, is parallel to PQ. That's the geometry behind the mean value theorem. Another way to think of it is that this, if you remember back to very early in the class, this slope of this line PQ is the average rate of change of the function f on AB. This f prime of C is the instantaneous rate of change of f at C. So another way to say the mean value theorem is that there exists a C in AB such that the average rate of change of F on AB, I'm writing this in orange because that is exactly this expression in orange. The average rate of change of F on AB is exactly this slope of this line PQ. There has to be a C in AB such that that average rate of change equals the instantaneous rate of change of F at x equals C. This is a point where it happened. Notice in our graph there's also a point here where it would have happened too. It can happen more than once, but it has to happen at least once. And so again, these are two ways that you can think of the mean value theorem. You can think of the geometry. The slope of the line PQ has to match the slope of the tangent line at least one point in between A and B. Another way to say that, the line PQ is parallel to the tangent line at least one point C in AB. Or equivalently, the average rate of change of F on AB at some point x equals C will match that instantaneous rate of change. Both natural ways to think of the mean value theorem. Now, how do we prove this? We take the following approach. Let's give the equation of the line. So the line PQ is, well, come back here. This line PQ is the line that goes through the point A, f of A, and it has a slope. We'll just call it m for the time being. So we have, we'll write it as y line minus f of A equals m times x minus a. So we're just calling it slope m for the time being, and it goes through the point f of A. So this is the point slope formula for getting the line. Now let's define a new function. We'll call it phi of x, and that's going to be the actual function. We'll call it y curve minus the line. Using our terminology, this means phi of x is, the curve was just y equals f of x, and the line was the quantity m times x minus a, and then we can just bring the f of a to the other side, plus f of a. Now, let's note something about this. And remember, we mentioned we were going to use Rahl's theorem. So let's check this at the endpoints. Phi of A equals f of A minus quantity m times a minus a plus f of a. And notice that everything here zeroes out. The f of a and the minus f of a cancel, and that a is 0. A minus a is 0, so this is 0. Let's look on the other end. Phi of b is, plug in b for x, f of b minus quantity, m times the quantity, b minus a, plus f of a. Recall the slope of that tangent line, m, was the rise over run, f of b minus f of a over b minus a. If we plug that in for m here, this becomes f of b minus, let's think about what happens when we plug this rise over run expression that we derived on the previous page in for m. The b minus a in the denominator will cancel with the b minus a in the numerator. And we're just left with f of b minus f of a. And now notice here your f of b's pair off to 0, and here your f of a's pair off to 0. And so we get 0. Now, Rawls' theorem can be applied. This function phi of x is differentiable on open interval AB and continuous on closed interval AB. So since phi is continuous on AB and differentiable on open interval AB. And by the way, the reason for that is because f of x has these two properties. And then what we're subtracting from f of x is just a line, which is, of course, continuous and differentiable for any x. So phi of x inherits those properties from f. But because of this, Rawls' theorem, remember what that said. That says that there exists a value c in the open interval AB such that phi prime of c equals 0. This will be our key. So, remember here that phi of x was equal to f of x minus m times quantity x minus a plus f of a. We're just rewriting that from the previous page. And we were just told that we have a c in AB with phi prime of c equals 0. Given this expression, we can calculate phi prime of x. So let's go ahead and do that. Phi prime of x equals, the derivative of f is just f prime of x. And now think about everything in this linear term. F of a is a constant. If you multiply this out, you get m times negative a. That's a constant. The only x term is this x, and its coefficient is m. So when we take the derivative of that entire term in square brackets, we just get m, which makes sense, because what's in square brackets is a linear term. But we mentioned that m was f of b minus f of a over b minus a. So now we have an expression for phi prime of x. Rawls' theorem guarantees us that there's a c in AB such that phi prime of c equals 0, which means we can take this c and plug it into our expression for phi prime. So combining these two means that phi prime of c is 0, but also phi prime of c we plug in c here. That's the only x appearing in phi prime of x. So we get f prime of c minus the quantity f of b minus f of a over b minus a. Those two are the same. They must be, this expression here must be equal to 0 because they're both phi prime of c, which tells us that f prime of c equals f of b minus f of a over b minus a, which proves the mean value theorem. So a bit of a longer proof, but again, one of the most important results in calculus, so it's something that we do like to prove. It's worth going through the logic a couple times to think about. One example I always like to give to explain the mean value theorem comes from driving. And this I find to be a very convincing and intuitive example. So suppose someone is driving on the Massachusetts Turnpike, the main east-west highway in the state of Massachusetts. The driver enters the Mass Pike at 8 in the morning using what's called Easy Pass at the Springfield, Massachusetts on-ramp. Easy Pass is a device that registers the time and the location that you get on the highway. At 8:30 a.m., so 30 minutes later, the driver exits the Mass Pike in Worcester, Massachusetts, and is registered with Easy Pass. And let's assume there's exactly 60 miles in between where the driver got on and the driver got off of the highway. Question is, what does the mean value theorem tell us? We do need to make an assumption. So we assume the position function of the car is continuous on that 0 to 30 minute interval. And it's also differentiable, which makes sense. The way that a car's position will change in time should naturally be continuous. You're not teleporting. It should be differentiable. You're never having jumps in velocity where you're going at, say, 10 miles an hour and then instantaneously you're going at 50 miles an hour. The car would tear itself apart in such a transition. So these are completely reasonable and realistic assumptions. So let's think about what you could say. Well, first of all, this driver was going pretty fast. We look at this and say, oh, the driver went 60 miles in a half an hour. So we know the driver averaged 120 miles an hour. So we can write that. The average speed, or the average velocity, is equal to the distance from Springfield at, say, 8:30 a.m. Or maybe if we do it in minutes, the distance after 30 minutes minus the distance at time 0 over 30 minutes minus 0 minutes. That's your average velocity, or your average rate of change of distance from the Springfield on-ramp. And we noted that's 60 miles minus 0 miles over 30 minutes, or 120 miles per hour. That's the average speed, average velocity. What the mean value theorem tells us is that there exists a time, we'll say t naught, between 8 a.m. and 8:30 a.m. at which the driver or the car was traveling at exactly 120 miles per hour. And the key word there is exactly. You can think of this as that's what the speedometer was reading. There had to be at least one moment where the driver was going exactly 120 miles an hour. You could make physical arguments that there were moments where the driver was going faster, because you can probably guess that the driver didn't get on the pike and get off the pike at a speed of 120. But the mean value theorem doesn't give us that. The mean value theorem says we can deduce with certainty that there was some moment when the car was going exactly 120 miles an hour. These types of driving examples are very helpful for understanding the mean value theorem. Let's look at a more textbook style example. Given the function x cubed minus x squared on the interval minus 1, 2, find a value of c that satisfies the equation in the mean value theorem. Well, we know that we have to get the derivative of f, so why don't we do that right away? F prime of x is 3x squared minus 2x. And we'll need to evaluate f at the endpoints. So f of b minus f of a over b minus a. B is 2, and a is minus 1. What's f of 2? 2 cubed, which is 8, minus 2 squared, which is 4. 8 minus 4 is 4. F of minus 1, we would have minus 1 cubed, which is minus 1. Here, when we square it, it becomes a positive 1. So we get a minus 1, or negative 2, all over 3, or 6 over 3, also known as 2. This would be one of the terms. Divide by b minus a here. This term would be equal to f prime of c. So f prime of c is 3c squared minus 2c. So we're simply plugging c in here. And in order to satisfy the mean value theorem, f prime of c has to equal this average rate of change of f over the interval minus 1, 2. So we now solve the equation 3c squared minus 2c equals 2, or 3c squared minus 2c minus 2 equals 0. And we solve this using the quadratic formula. So we have a equals 3, b equals minus 2, and c equals minus 2. And remember our quadratic formula. C will equal to negative b plus or minus square root of b squared minus 4ac all over 2a. In this case, negative b is minus minus 2, or 2, plus or minus. B squared is 4. A times c is 3 times negative 2, or negative 6, times negative 4 is positive 24. 2a is 6. So we have 2 over 6 plus or minus root 28 over 6. Or 1/3 plus or minus 28 is 7 times 4. So the 4 comes out as a 2. So this is 1/3 plus or minus root 7 over 3. Both of those values actually do fall within the interval negative 1 to 2. So 1/3 plus root 7 over 3 is approximately 1.21. And 1/3 minus root 7 over 3 is approximately minus 5, 4, 9. And again, both are in -1, 2, so both qualify. So at these x values, the instantaneous rate of change of f matches the average rate of change of f over the interval -1, 2. So this is an example of how we use the mean value theorem. We will use the mean value theorem more. It's one of its main powers in this course is that the consequences of it give us very, very strong tools, including the theorem we mentioned earlier, that if a function that's differentiable has a positive derivative on an interval and it's increasing on that interval. So we'll actually see some of the consequences of the mean value theorem and its further use in the next lecture.